We're in a golden age of Mars exploration. So this year alone, 3 space missions have arrived at Mars. One from the UAE, one from China, and one from the US, NASA. So that combination is a wonderful one, actually looking at Mars. And actually we have another mission going next year. So on the right-hand side, we have an image of the Rosalind Franklin rover. So that is the one which we're working on. So that's for launch next year in 2022 in September, and that will arrive in June 2023. And that carries with it a panoramic camera system, which sits at the top of the mast there, so the top of the mast. And just to give you an idea, I brought actually along a model here of PanCam. So this sits at the top of the mast of the rover, and it's about that high above the Martian surface. So 2 meters above the surface, and looks around and looks potentially for evidence of life. But it's not only the camera system, there are many other instruments which will be doing that, and I'll come to that later. So I'm going to start by talking about the 3 missions which have arrived this year. So February at Mars, February 2021 was very busy with 3 missions arriving one after the other in February. And just to introduce you, I'm going to tell you about why we're so interested in Mars. One of the reasons is that life might have started on Mars 3.8 to 4 billion years ago because conditions were somewhat similar to Earth. And that's about the time that life was starting on Earth as well. So we have that interesting prospect for looking for life on Mars. But there are other things we want to do with Mars as well to try and understand Mars as a planet, why Mars is different to the Earth. And so the missions are looking at all of these types of things to understand those possibilities. I have to say that Mars is not the only place where there could potentially be life elsewhere in the solar system. At the moment, we only know of life on Earth. We don't know of life anywhere else in the universe. And so elsewhere in the solar system, as well as Mars, which is a really good prospect, there's also Europa, one of the moons of Jupiter, which has water and the right chemistry going on in a subsurface ocean. There's also Enceladus, one of the moons of Saturn, and possibly Titan as well. So there are these other locations in the solar system which are also fascinating. But Mars is of course closer, easier to get to, and we think there was a possibility of life. So 3.8 billion years ago, we think that's when Mars was really habitable. And there's a number of strands of evidence for that. So first of all, Mars at that time had water on the surface. There's lots of evidence been building up for that from orbiters which have been orbiting the planet for a long time. So starting in the 70s, in the 1970s, the Viking orbiter, which was in orbit around the planet, that was saw outflow channels on the surface, and so that's partly evidence for, it's sort of indirect evidence for ancient water on Mars. And that evidence has been building up with the more recent missions as well. So water played a key role. And more recent missions actually have really sort of proved that it was water on the surface of Mars causing these outflow channels. And in the image on the left there, you can see effectively an outflow channel, which is an ancient flow of water on Mars. That particular one is from the European Space Agency's Mars Express orbiter, which is still in orbit around Mars. So another big thing 3.8 billion years ago which Mars had is a magnetic field. So we have a magnetic field on Earth. Of course, we used to use that for navigation. Everybody now uses GPS, of course. But the image here is actually evidence for crustal magnetic fields on Mars, which were left over from when Mars had a global magnetic field. So our magnetic field helps to keep in our atmosphere, and this is one of the sort of reasons we have life on Earth. And it's a sort of cradle for life in a way, sort of keeping the Earth safe from the solar wind blowing away the atmosphere, which has happened at Mars, because Mars lost its magnetic field. But we also have the possibility for stopping radiation from space actually coming to the surface, and that's another thing which a magnetic field can do. So the image here actually shows the color scale is a height map of Mars. So you can see the blue is the sort of low areas on Mars, and then going through red and up to white, which gives you the highest areas. And so you can see the northern hemisphere is mainly quite low. The southern hemisphere of Mars, this is a map, the southern hemisphere of Mars is relatively high, and in fact over the top of that color map are black and white contours, and that's to do with the magnetic field. So these are crustal magnetic fields. So these old rocks, we know the rocks are old because of the number of craters, the cratering density. You can tell the age of surfaces in the solar system from that. And so it was an ancient magnetic field, 3.8 to 4 billion years ago. But Mars suddenly lost it like that. And so it suddenly lost its magnetic field. We think that's because Mars is smaller than the Earth, so it lost its heat of formation more quickly. So the core, which we have a rotating core underneath us with iron, which means that we have currents flowing, and that produces the magnetic field. That stopped on Mars because Mars is a bit smaller than the Earth, about half the size. So that's why Mars's magnetic field stopped. But this is evidence for that magnetic field, for the ancient magnetic field, which used to be on Mars 3.8 to 4 billion years ago. So the other thing it had at the time was volcanism. This is a picture of one of the biggest volcano in the solar system, called Olympus Mons. And so this is 27 kilometers high, 3 times the height of Mount Everest. It's huge. It's 600 kilometers across, but it's extinct. And so there used to be volcanism, helping to provide water cycle and things like that on Mars. So we think 3.8 to 4 billion years ago, before we lost that magnetic field, we had a habitable planet at exactly the time that life was starting on Earth. So we think there's the possibility of starting life on Mars at that time as well. So the next slide shows what Mars might have looked like 3.8 billion years ago. This is according to computer models and so on. So on the left-hand side, you see something which looks a little bit like the Earth now. It had a thick atmosphere. It had water clouds in the atmosphere, water potentially on the surface in those low regions on the map. There may have been an ocean in that northern part of Mars, and certainly lakes. There's evidence from the rovers that long-lasting lakes were there on Mars with the right kind of pH, the right kind of acidity to actually be habitable as well. And so at that time, Mars had that habitability. Mars now, on the other hand, on the right-hand side, is a cold, arid place with a very thin atmosphere, less than 1% of the Earth's atmospheric pressure. It's a carbon dioxide-rich atmosphere, so it's not suitable for life. And actually, the surface temperature is extremely cold on the surface of Mars, so 5 to 10 degrees centigrade during the day, but at night, every night, it goes down to minus 100 to minus 120 degrees centigrade. So every night it's doing that. So anything we put on the surface of Mars has to survive that cold temperature on the night side of Mars. And the Mars day is just a little bit longer than the Earth's, about 24 hours, 40 minutes. So it's rotating a very similar type of rate. Okay, so Mars now has is not a very good place to be, not a good place to live, and we think the possibility of life on the surface is actually zero. It's really not habitable at all. But at depth on Mars, we might have evidence for past life, and so that's what we're looking for. One of the things we're looking for with the missions. So our requirements for life, for life as we know it, we know that we need liquid water, we need the essential elements, the right chemistry going on. So this is carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. We need a source of heat, so to make reactions happen, and we need enough time for life to develop. So we need all of that for that's the sort of recipe for life, and early Mars had that, as indeed did those other places in the solar system, and may even have now. So Europa and Enceladus seem to have conditions right now. So that's future missions, including the JUICE mission launching next year. We'll be looking at the Jupiter system. Okay, so on to what the missions are happening at the moment. So the missions to Mars, and the talk mainly is about the 4 missions here at the top. So the UAE have the HOPE orbiter, which arrived in 2021. This was launched last year. So every 2 years, you have the opportunity to launch to Mars. So our mission is launching next year. But HOPE arrived actually on the 9th of February this year. So that was the first of this year's missions to actually arrive in orbit around Mars. That's the HOPE orbiter. And I'll talk a bit more about that in a moment. China has a mission as well. So the Tianwen-1 orbiter, that arrived in orbit around Mars on the 10th of February. 2021, so just one day after the UAE mission. And that actually has a rover, a little rover as well, which is on the surface of Mars. It landed successfully in May this year, so that was deployed from orbit and landed on the surface, and I'll show you some of the results from that as well. And then NASA have the Perseverance rover, sort of very excitingly landed on Mars on the 28th, in February 2021 as well, the 18th of February 2021. So the Perseverance rover and also the little Ingenuity helicopter. So I'll show you some of the results from that as well. And then next year, we have the ESA-Russia, European Space Agency in Russia, Rosalind Franklin rover being launched next year. And as I say, that arrives in June 2023. And also, there's a number of other missions. So actually, we have 11 missions altogether at Mars, which are at the moment sending back data. So Mars Odyssey, Mars Express, Mars Reconnaissance Orbiter, Mars Science Lab, otherwise known as Curiosity, the Mars Orbiter mission, the Indian mission, MAVEN, the ExoMars Trace Gas Orbiter, and also InSight, which is looking at the inside of Mars. So it's a really exciting time for Mars science, and as I say, a golden age, really, of Mars exploration. So the first mission to arrive was indeed the UAE mission. So that's the Emirates Mars mission. And this is one of the instruments. It actually has 3 instruments on board. It's an orbiter, so it's an orbiter around Mars taking images, but also it's sort of a weather satellite, the first weather satellite we've really had at Mars. So this is looking at all aspects of the atmosphere of Mars, looking at the and how it interacts with the surface, and how it interacts with its space environment. So it's looking throughout the atmosphere to be able to do that. So those 3 instruments, there's a visible imager, which this is an image from that. So this shows Mars with Olympus Mons. Don't need to point it out, it's a blob on the right-hand side. That's the very large volcano. So very nice imaging system, which is working well. They have had quite a few other results here. So from the ultraviolet spectrometer, and an infrared spectrometer. So between the instruments, these are actually looking at different aspects of the atmosphere using different wavelengths of light. And so those use those different wavelengths to look at different aspects of the atmosphere. But one of the key results, and really interesting results, actually comes from the ultraviolet spectrometer. And that is to look at the Mars aurora. Now, this is fascinating because Mars had a magnetic field. It now doesn't have a global magnetic field. It has crustal fields on the surface, so little blobs of magnetic field on the surface effectively. And these have been imaged now with the HOPE orbiter. And so we can see that here. So the images show on the day side of Mars is the sort of bright green blob on the left-hand side, and then the night side is the darker patch with making up the circle, but with the individual areas of aurora. So the aurora, this is a bit like the northern lights and the southern lights which we have at Earth, but with the magnetic fields of Mars, these crustal magnetic fields, we can now see how those are located on the surface. Previously, the measurements using magnetometers showed us the shapes of them. So what's happening here is the solar wind is a stream of particles coming away from the sun all the time, about 1 million tons per second. And these can get into planetary environments. So at our planet, it produces the northern and southern lights, the aurora on Earth. At Mars, it interacts with these crustal fields and sort of that guides the charged particles down, because of course there's a magnetic field, charged particles, they're guided down and hit the thin atmosphere of Mars. And when they do that, they produce light, and so that it's ultraviolet light. And you can see these shapes here, which is shown by highlighted by the circles. Those are the signs of those crustal magnetic fields. And this is what we call discrete aurora. So this is discrete parts of aurora. That happened to Earth as well, but more towards the poles of Earth, where the northern and southern pole, where we have the aurora. Here it's happening sort of at the various places where we have crustal fields on the surface of Mars. There's also something called diffuse aurora and proton aurora as well. But these are the best images which we have so far of the discrete aurora. So the UAE mission is producing that. We had a session at the Royal Astronomical Society's National Astronomy meeting earlier this year in July, and this was one of the exciting new results in our Mars session from the UAE mission. Okay, so the next image is from the next mission which arrived. So, another day at Mars, another mission. So it's the 10th of February when this arrived. And so this went into orbit and produced a number of images of Mars. So, of course, the usual image of Mars on the right-hand side there. And then on the left-hand side, more detailed images. And there are some amazing images and also other data. So the orbiter is very well instrumented with several different instruments looking at not only imaging, but also looking at the magnetic field environment, looking at the escaping particles from Mars. So it's very much in the line of international space research going on. So some exciting collaborations are possible with the Chinese for this as well. So this is from the orbiting mission, and that successfully went into orbit. These are some of the images from it. And then they also have this lander which landed on the 15th of May this year. So this is their first attempt to land on Mars, China, and it worked very well. And so we can see on the left-hand side, those are the ramps that the rover actually went down to get onto the surface of Mars. And on the right-hand side, an image of the rover itself. So showing some really amazing images from the area which they landed. And another image produced relatively recently, again showing some wind-blown structures and some of the geological features on Mars, as well as some of the antennas associated with the spacecraft itself. So again, the rover has a number of different instruments. It has not only images like our PanCam, it's not that one, but images made in China. And then there are also some other instruments, including a subsurface sounding radar, so that could look underneath the surface to look for hydrogen and water underneath the surface. And that, so this image is amazing. This is a selfie of the mission actually taken on Mars. So they had a little camera unit which they dropped on the surface, and that with the rover, and then the rover sort of wheeled back a bit, and you can see the selfie of the rover and the lander. So amazing image to be able to see that. And they, of course, also took images during the descent. So just like with the Perseverance rover, which we'll get to in a minute, these are pictures from the surface, but they also took pictures on the way down, so you can see parachute deployments and so on. So those are available for people to look at. And again, there's interesting results coming out from this, which are starting to appear in international conferences. It's a very international thing, space science. So working with China with their data, we've helped to do that. And again, with our session at the National Astronomy meeting, we had some of the scientists presenting at that, which was great. So the next slide shows Perseverance. So this is the third mission arriving at Mars this year, and it arrived on the 18th of February. It went into land. So this is a slightly complicated picture showing all the instruments on the rover. The rover is a little bit bigger than the one which we're sending next year. It's more of a car size, so it's a sort of 1 ton of lander, which landed on the surface of the rover. Landed with a very exciting descent sequence, which some of you might have seen, and that was available in real time, just about, and so that was amazing. But successfully landed, and those are the instruments on board. So what this is doing is to look on the surface for potential signs of life, and underneath the surface, but it's drilling cores which will eventually be brought back to Earth. And I'll show you the picture of the first sample which has been taken, which will be coming back to Earth in a few years' time. So, as I say, it's a really exciting time in Mars exploration. So just to introduce you to the Perseverance mission, this is the crater, Jezero crater, where this landed. This is an ancient area on Mars with water flowing into it and water flowing out of it. So on the left-hand side there at the top, beside the crater rim, you can see signs of a river delta, and that a river delta going out into the crater, and so that's one of the targets for this mission. Also, water flows out of this on the other side, or flowed out of it. And again, this is 3.8 to 4 billion years ago when there was water on the surface. So we know that there's water on this crater. This crater actually was made by a meteor hitting Mars, sometime before that, of course, but the crater was the right shape to sort of fill with water and then for water to flow out of it. So it's a good place to be looking for potential biomarkers, because if there was life on Mars, that water might well have contained it, and so that's one of the reasons for going there. So the actual mission landed in the region where that oval is, in fact, a very precise landing, which just in one of the spots to the right-hand side, or just towards the right of the center of that oval, is where it landed. So we're lucky enough to be involved in this, in the science of this. We're on one of the instrument teams, the Mastcam-Z team. So again, that's a camera system on the top of the mast, led by my colleague Jim Bell, Arizona State University, and we have a few UK scientists actually involved in that camera system. So very exciting mission. That's where it landed, and the idea is that this will eventually rove to that river delta. And so that's a really good place to, sediments would have been laid down. It's a good place to be looking for potential biomarkers on Mars. And as I say, the idea is to actually store samples from Mars in tubes for later bringing back to Earth. So this was the exciting landing sequence, and so this is just a still from that, which is amazing. The rover being let down from its sky crane system. This is the way it landed on these sort of a bit like a puppet on a string, but being lowered down to the surface safely, worked extremely well. And of course, has taken a number of images. But actually, before it landed, this is an image from the Mars Reconnaissance Orbiter of Mars. So in the background, you can see the image, and then a blown-up part of it. That is the parachute and the rover before it actually landed. So that's taken from orbit. So to be able to do that, to get the timing right and everything, was just amazing to be able to see that before it landed. Okay, and that's the landing, after the landing, and showing the sort of dust kicked up by the actual landing system, because it's on. The sky crane has retro rockets, quite powerful, to hold the thing above the surface. Then they cut the cords and fly away into the sunset. So we have an amazing landing. Okay, so this is the location where the landing actually is, with a very high resolution image of Mars. So you can see the green dot in the middle there. That is where the landing occurred. Over to the left-hand side at the top, that's the remnants of the river delta, and there's another part of that towards the center left of the image, the sort of brighter part there. That's the remnants of an ancient river delta, and so that is where we will be roving to eventually with this rover. For the moment, it's sort of gone south and then a bit west. I'll show you a map a little bit later on. But when it first landed, this was the first panorama which it took. And this is really high resolution. This is from the Mastcam-Z instrument, so Jim Bell's instrument on Perseverance, and shows and this is very high resolution. You can look at this on the web, you can zoom in and look at features, and you get an idea of the detail by that inset there, which is one of the rocks in the far distance. So really detailed, wonderful images from the surface. And so that was one of the first pieces of data to come down, which showed that it landed in an amazing location. And the top image there shows actually that was all pre-programmed before the landing, because while you're landing, you're out of contact with the Earth. So it's not like being able to control, a computer game or something like that. Everything has to be done automatically. So one of the things which is done automatically is taking that panorama sequence. So you've got to work out how it's going to land, give enough idea for the right direction to look. And so those red things over the top are the individual images which were stitched together to make that amazing panorama. And all that pre-programmed before the actual landing. So some other images on there from other features. So after landing, some amazing images from all of the cameras, but including Mastcam-Z and the navigation cameras and SuperCam and all the other instruments which are working really well. So this is another selfie showing the rover, and you can see, well, you wonder how did it do that? Well, it's by combination of, it has a long robotic arm with a camera on it, and so you can do that. If you take enough pictures, you can sort of, not see the arm which has done that. But in fact, that selfie shows not only the rover itself, which you can see with the rotating head there, and that shows the pan tilt mechanism which they have for the camera, but also on the left-hand side, that's Ingenuity, which is a little helicopter. So this is the first time a helicopter has been sent to Mars. This is the Ingenuity helicopter. It's only 1.8 kilograms, so less than 2 bags of sugar is the weight of it. It's about 50 centimeters high. It's got rotor blades which counter-rotate. There are 2 of them at 2,400 RPM. Because I mentioned that atmosphere of Mars is really thin, so it's less than 1% of the Earth's atmospheric pressure, so you have to have very rapidly rotating blades to get enough lift to get the thing off the surface. And so that's the Ingenuity helicopter having been put onto the surface. And this is a video, actually, of the first flight of a powered vehicle on another planet. And so this was an amazing Wright brothers moment. You can see there the rotor blades rotating on the image. Ingenuity itself is at the bottom of the plot, and there it goes above the surface. And this is its first flight, so it went basically up and down again, which is fantastic. So this was effectively to show you could do the engineering to actually fly something in such a thin atmosphere. So this is an amazing technological achievement. There it is landing again. So it has a couple of cameras on board which take images, and in fact now this is being used as effectively a scout for the rover, for the main rover. So we have, that flies out in front, decides where to try and explore. So that wasn't the original intention. The original intention was just to do the engineering side of it, to show that you could do that. But now it's still working, so why not? It's already made 13 flights on Mars, and so and still scouting in front of the rover effectively to look for good places to go. So it's in the process of doing that. These are some of the images from that camera system and from the 2 camera systems on board that little helicopter. And so there's a black and white camera which you can see, and that's fast enough to give you an image. This is an image of its shadow, its own shadow on the surface. So you can see the rotor blades, and that's the shadow on the surface. On the right-hand side is the color camera. And actually on the left-hand side of the color image, you can actually see the rover as well. So that's flying a little bit away from the rover. So that little blob on the top left there is where the rover is. And as I say, that's being used now to enhance the science. Okay, so some amazing images. This one is an image of the crater rim. So I mentioned this is a crater. It's an ancient crater on Mars, which was filled with water, and this is the crater rim. So this is a relatively high crater rim in the distance. And then this image and a little video shows them trying to take the first sample on Mars. So this is a robotic arm which has got a number of instruments on it, including an abrasion tool to abrade away at the rocks, and then you can do detailed analysis of where you're going to take the sample. There is also a drill and a coring mechanism to actually get a core, and that can get cores up to 6.6 centimeters from underneath the surface. So again, it's getting underneath the surface, but not as deep as we're going to be doing with Rosalind Franklin. But nevertheless, these are the samples they're getting, and that's the sampling mechanism. So the first rock which was sampled was carefully chosen after a drive from following the flight of the helicopter and the testing of that to an interesting scientific site, and they chose this rock. Now these are called Paver Rocks just because they look a little bit like paving stones, and you can see this is the first the drilling has been done, and these are the sort of spoils that come out from the drill. They tried to take a sample with this, and unfortunately that didn't work on the first thing. There's a better picture of the rock, of the actual hole in the rock, and some little indentations on the side there. That's to do with lasers, which can zap the rock, and looking at the light which comes off, you can tell the chemistry of what the rocks are made of. So that's looking at the light which is emitted by those laser zaps, and you can see the evidence for that. So that it looked good, looked as if the sample had been taken. Obviously, a sample has been taken out of there, but it turned out, so, oh yeah, that's the abrasion tool to actually get the, and coring tool to get the sample of the rocks. And but unfortunately, that first one, this is the the sample tube, which the idea is to bring those back to Earth. But unfortunately, the first one was empty. However, the good thing about that is that it's a sample of the Martian atmosphere, which is going to be brought back to Earth. And so, you know, we can still get some good science out of that particular one. But it was a disappointment. And that appears to be because the rocks in that location seem to be a little bit less, or a little bit more crumbly than had been expected. But actually, that's a really good location because there are sort of flecks in there which look like salts have been left, more so than we get at the other site. And so I'll get to that in a minute. Okay, so this is a map showing where the rover has been. So the scale bar on the bottom there is 200 meters. At the top is the landing site, the Octavia E. Butler landing site. That first sample was taken at this point on the bottom part of the sort of V there, Rubion, so that location. And then the rover moved along to this area called Citadel to take its next sample. And so that's the sort of context. Now, all of this is kind of quite small in the crater. The actual river delta that I was talking about, that's a little bit sort of north of here, but there are some parts of that also in this location. The rover is currently looking just in a little, what they call a toe dip, just into the terrain up onto that ridge, so it's currently doing that. But the second sample was taken at that location called Citadel. And this is a sort of panorama of where the second sample was taken. And actually, it's that rock which is on the bottom to the left there. It's that rock which the sample was taken from. So there's some more, and there we go. So there's some more images of that. So there's the rock, which was carefully selected. These are sort of sedimentary type of rocks, so it looks like they've been laid down in the past, but some analysis was needed to see whether these were volcanic or other processes. So that's the rock again in a bit more detail. And then this, after doing some abrasion, so on the right-hand side, you can see a little bit of an indentation. So that's where the rock is abraded, and then you take other instruments up on that robotic arm to actually do the analysis. And so that was done. And then the hole which you can see, that's the first sample which was then taken and successfully put into a sample tube. So on the left-hand side here, that's the sample, this time in the sample tube, so that looks good. So on the left-hand side, everything looked fine. The one on the right-hand side, they did some sort of preparation for bringing that back to Earth, including shaking it to get some of the dust off the front. And it looks like the sample has gone, but actually it hasn't. That's the good news. It's still in there. And in fact, there is a better image where you can actually see the sample. So this is another historic image from this mission. It's the first sample which is going to be brought back to Earth. And so that's the first sample which was taken. You can see there's a number of different colors in that sample of the rock, so sort of brownish and blackish and the whitish flecks. So all of those are interesting. And those, when looked at in more detail, you can tell the types of things which are there. Oh yeah, that's just another image showing the in focus the sample at a particular point. And there's the sealed sample tube. So that sealed sample tube is going to be, for the moment, kept in the rover. There are about 40 of these altogether. They're going to be dropped off at a particular location on Mars at some point fairly soon. And then another cache will also be left on the surface for another mission to go back later, and I'll get to that in a moment. But for the moment, some of the scientific analysis which has been done with instruments on the rover called Watson and Sherlock, you might notice, these are acronyms which stand for very technological things, but actually Watson and Sherlock, we're looking at detective work here, to try and understand the features on Mars and what we're trying to do. So on the left-hand side is the general image. Again, you can see some of the rock grains. Now, some of those are sort of triangular If it was to do with water, you'd expect maybe it would be, if it was laid down by water, you'd expect circular shapes, but they seem to be triangular shapes. So these seem to be volcanic rocks, which is interesting. But the little flecks in it, the sort of whitish flecks, those seem to be salts. And in fact, on the right-hand side, those are things like sulfates and phosphates, things like that, which in this sample. So this is the abraded patch of the rock, and then the sample was taken later from just a slightly different location on the rock. But this is a really, the science team love this because it's got salts in it, and so the salts mean that those could have been laid down by water, and if you have biomarkers, that would be a good place for that for those biomarkers to be. So another image here from the Pixel instrument, and so that again looks in detail at the chemistry. In fact, the yellowy parts of this image shows salts on the surface. So this was shown at the NASA press conference just over a week ago. Okay, so the samples that shows where the abrasion patch was on the sample there on the bottom. That is where those abrasion features were taken, and then the samples were taken, and you can see eventually 2 holes. And so the idea now is to actually have 2 samples, so one from each place at the moment, and so the samples from the 2 samples from this rock. One will be put in that first cache for potential bringing back to Earth, and the other one will be put in the second cache. So doubling up of samples is what they're doing to make sure they can get the information back. So again, this is the same map we saw before. So the second lot of samples were taken from this location Citadel, which you can see on the left-hand side there. And as I say, it's currently exploring the ridge just above that. But that second set of samples was taken from there. As I say, really historic, because these will be the first samples to be brought back to Earth. And in fact, this is a complicated diagram which shows you how difficult it is to get the rocks back to Earth. And so there's actually 3 launches of spacecraft. So at the bottom you can see launches. So the one on the left-hand side is the Perseverance rover, which is currently on Mars. Mars 2020 is the other name for it. So that is currently on Mars. It's collecting its samples. So we need 2 more launches to be able to actually get the samples back. So the first one there is a spacecraft which will go to Mars, land on the surface, taking another rover with it. This is called the Sample Fetch Rover. And so that rover actually is going to be built in Stevenage in Airbus, not too far from here. That's the European Space Agency's contribution to that mission. You can see there's a little E, which is the ESA logo on that rover. That collects the samples and then brings them back to the lander. Then these are fired off the surface of Mars because, of course, they're held down by gravity, so you've got to get off Mars, and so we do that with the rocket, which is shown there. And then that is brought into orbit and then eventually brought back to Earth and brought in a capsule back to Earth. So there's a few artist's impressions which I'll just go through very quickly for this Mars sample return mission. And I'll say, this is joint between the European Space Agency and NASA. So there's the Perseverance rover, an artist's impression of it, with its sample tubes on the surface. As I say, a total of about 40 altogether. The idea is to bring those back to Earth. The next one shows that next mission arriving with the little rover on. So this is not as sophisticated as the rover which is there, or compared to our rover going next year, but that lands on the surface with retro rockets like that, and that's the Sample Fetch rover on the top. There's the Sample Fetch rover about to get those same tubes, gather them up, take them back to the landed platform, and then eventually launch them off into orbit. So there's the little rover taking the samples to the landed platform, and eventually launching on that rocket off from the surface of Mars. It looks like science fiction, doesn't it? But this is a real design for a mission which is going to be doing this. So this is going to be going in 2026 to the first of those missions, and then eventually we expect the samples back on Earth by 2031. This is another sort of the gymnastics you have to do in orbit to be able to dock and then put the samples into a capsule which eventually comes back to Earth. And the reason we want to bring samples back is to use facilities on Earth which we can only use on Earth. So this particular one is the Diamond Synchrotron at Harwell. So this, you can see from the diameter of that, that is not something you could send to Mars. Okay, so, and that is one of the devices, and devices like that will be used to analyze these Mars samples. There's a certain amount we can do on the surface of Mars. We can't do everything. Earthbound laboratories are, of course, much more accurate, and we can get much more detailed analysis from them. So we'll be doing isotopic analysis, all sorts of things like that. And so in the US and UK, Europe, there'll be a lot of interest in actually looking at these samples. And that's one of the facilities. And that nicely illustrates why we can't send something like that to Mars. It's much too big. So, okay, now this is a nice map. This is where landing attempts have gone on Mars. And so the ones in sort of lighter script are ones which have not worked. The ones in solid script have worked, and so we can see opportunity, and we can see the various missions. Mars 2020, which has now successfully landed. Beagle 2, unfortunately, did land, but didn't send us any data back. But you can see that's the location of the various landers on the surface. And actually, just to the right of Mars 2020, in the Acidus Basin, that's where the Chinese mission is, the Zhurong rover. And so that rover is doing interesting investigations there. So that just gives you a sort of summary of the landing sites on Mars. And our ExoMars rover is shown, that's the other one in blue towards the left-hand side. So we will go into a place called Oxia Planum, which is another place where there's been evidence of water on Mars in the past. Which brings us to our rover. So this is the one which is launching next year that I'm most excited about, because with this, we're going to be drilling under the surface up to 2 meters. So bear in mind, the American mission at the moment, that's drilling 6.6 centimeters. We're going to be drilling 2 meters underneath the surface with Rosalind Franklin. So the rover, it's the ExoMars 2022 rover, but it's now called Rosalind Franklin for reasons we'll go into in a minute. This is the payload for it. So on the top left is PanCam. That's our panoramic camera system. As I say, this is the one. This is a model of it. This sits 2 meters above the surface of Mars like this, and so that is going to be giving the geological and atmospheric context for the mission. There's also, on the left-hand side, those are all context instruments. So there's an infrared spectrometer, there's a subsurface sounding radar, there's a neutron experiment, which is going to be looking effectively at hydrogen in water underneath the surface, and there's a close-up imager. That's a bit like a geologist's hand lens. Then in the middle, the vertical thing, that's a MARMIS. That is a little imaging system actually inside the drill itself, inside the tip of the drill. So that gets the geological context from where we're actually getting the samples from. And then with this mission, we analyze them on the surface of Mars. And so those three instruments on the right-hand side, those are the ones that we analyze the actual samples that we get from 2 meters underneath the surface. That's where the ones that we use to analyze those. So, and that's micrometer, a Raman spectrometer, and a Mars Organics mass analyzer. So there's big UK involvement in this mission, of course, in both in the academics field and also in industry. So I'm the lead of the PanCam instrument, which is on the top left there. That's getting the context. But University of Leicester are involved in the Raman spectrometer, which is on the right-hand side. One of the things actually looking at the samples. And actually, we have a joint meeting with them later this week to discuss plans for analysis. So it's a very exciting payload. The actual rover itself is shown here. So this is, we're looking for signs of life on Mars. We launch on the 21st of September 2022, so next year now. So in fact, the 20th, depending which time zone you're in, it's actually 1 year today is when we're launching this. So 1 year today is when our mission goes to Mars, so very exciting. And then landing on the 10th of June 2023, and we're drilling up to 2 meters underneath the surface, and we have both context and analytical instruments. So that's the combination which we have. And I should say this rover was built in Stevenage as well. So Airbus in Stevenage won the contract to do that for the European Space Agency, working with Thales Alenia Space, who are the prime contractor for the whole mission. So we have a very good UK industrial and academic involvement in this rover. So very exciting. Why is it called Rosalind Franklin? Well, it's after, of course, Rosalind Franklin here, so brilliant X-ray crystallographer who did her work. And she took this amazing image, photo 51 of a fiber of DNA. So that was really instrumental for the, critical for Watson and Crick's discovery of the double helix. So they got the Nobel Prize for that. Of course, this photo was very key in that. And she's done other very important work on the structure of carbon and viruses. That is the photo 51. So I can't wait to see what our 51st photo on Mars is going to give us. We'll see. But anyway, it's a very exciting thing. And so the UK Space Agency had a competition to actually name the rover, and they got something like 36,000 entries for it. And this was the winning one. So and absolutely very apt. And so we call the rover after Rosalind Franklin. So why do we need to drill? So the NASA mission, as I say, is drilling 6.6 centimeters. We're drilling 2 meters. And actually, we've done some drilling tests in the last few days. Those are going on in Italy at the moment to actually test the rover and the instruments working together. This is a test model of the rover. It's not the actual one. But that successfully drilled down to 1.7 meters and got a sample out successfully from underneath the surface in Italy, so that's great. But why do we need to do that? So we're getting below where destructive agents can sort of would be a problem for organic samples like biomarkers. And so we need to get below about 1 millimeter to get below where ultraviolet radiation can get to. We have this very thin atmosphere of Mars, so this means that it's a very thin atmosphere, so it's a bit like being under. It's a bit like being under an ozone hole all the time. So you get the ultraviolet from the sun, which can get to the surface of Mars, and so that is very destructive for life. And so the very surface layer, we have to get below that. We have to get below about 1 millimeter to get below that. There are also oxidants down to about 1 meter, and then penetrating radiation, ionizing radiation, both from the galaxy and from the sun, solar energetic particles, which happen every so often. And the study of space weather is all about that, predicting those events. But we need to get below about 1.5 meters to be able to do the samples. I actually had a PhD student working with us a few years ago who did those calculations, and getting below 1.5 meters is what you need to do. And so 2 meters is great. The 1.7 meters, which has successfully been done, is also good. To be able to get that sample. So that's what we'll be doing on the surface. Okay, so this is where we're going to land. This is Oxia Planum. So again, this is on this color map type of thing of the surface of Mars, and again going from the blue, which is low areas, through green and up to yellow and red and white, which are the highest areas. So on the left-hand side, we can see that is the context for where this is. It's a little bit of a different position on the surface, as we saw on that previous slide, to where Mars 2020 is. That's a bit further round towards the Isidis Basin, which is where Tianwen-1's lander, the Zhurong rover, is working. But this also, there's evidence for water having been involved here. There's phyllosilicates on the surface, which are clays, and there's evidence for water having played a long role in the history here of the surface. So the clay-bearing rocks, actually, it turns out, are about 3.9 billion years old in this location. So just a little bit older, probably, than the Jezero crater landing site, but very close in time. So they're both really, really good places to be looking. And we see the remnants, again, of a fan or river delta in this region as well. So this is a great place for us to land. And we had a long process to actually choose the landing site. Okay, so this, I'm so proud to be able to show this. This is the flight model. This is the actual rover, which is going to Mars. And so this was taken during some of the tests in 2019, November 2019, which were done in Toulouse after building it in Stevenage. So it went to Toulouse, and it's now in Turin, and on its way actually today, I think, to Rome to do some bake out. But this was while it was undergoing its testing in Toulouse. So we can see PanCam, so that's the optical bench. This is a model of it here, and we can see that on the top of the mast. The solar panels, the drill is the black thing on the front, and then the wheels and so on. So we have also, as well as the optical bench, which houses the 3 cameras, and I should explain, we have 2 wide-angle cameras, which are separated by 50 centimeters. So these are wider separated than the human eyes, so we get very good stereo from that. Each of those has a filter wheel in front of it, which we're able to get geology and atmospheric science. Then we have another camera, the high-resolution camera, which looks in detail at rocks. And so that's the technology which is packed into this, this optical bench. Then we have things to make sure we get the colors right. So we have a calibration target there, which is the colored set of patches. That is placed on the front of the solar panels on the rover. And so that helps us to get the colors right. We have fiducial markers to help us get shapes right, so geometrical calibration. And then we have a rover inspection mirror, which we can look underneath the rover itself, and so to see if there are any obstacles and things like that. So this is one of the instruments, but as I say, it's the one which we're particularly proud of. So this is just a little bit more about that. So these are the filters. So with these filters, and these again are the actual filters going to Mars. So these are the ones on the flight model. So those are the actual filters, and those are the wavelength ranges of them. It basically is visible part of the spectrum and going a little bit into the infrared. We have some wide filters for red, green, and blue to get color, and then we have narrow filters for geology. We had a PhD student helping us to actually select those filters. And then we have some atmospheric filters as well. And so we're looking actually at the sun. These are called solar filters. And you're looking at the sun and looking at, there's an absorption dip of water, and with a particular wavelength, you can get the amount of water between the sun and us. So we're able to look at water vapor in the atmosphere as well as dust. So we've packed as much science as we can into basically what is a camera instrument, and very excited for it to be going to Mars next year. So just to finish, we're currently in a golden age of Mars exploration, as I've tried to explain. So we have currently Hope Tianwen-1 with its Zhurong rover, Perseverance and Ingenuity. All of these arrived this year, 2021, at this launch opportunity. As I say, it's joined the missions which are already there. And then it's already taken 2 samples. It's about to take another one, we hope, which is going to be brought back to Earth. These are already cached, ready for the Mars sample return mission, which will be 2026, getting back in 2031. And next year, we can't wait for the Rosalind Franklin rover to be launched. We have the team is ready, able to get the data. And in fact, I should say, this is a huge team effort. So at the bottom, these are the institutes which have helped, the ones with a few people involved which have helped and will be helping with the science as well. Those are at the bottom of the slide. It's a big team effort of scientists and engineers working together internationally. So we have 9 countries on the science team, engineers which have built the instrument and made sure everything is right, including the engineers which built this model. This is a very accurate model of the camera. So we can't wait for this to look at the new dimension on Mars, drilling 2 meters underneath the surface. So I'll stop there. Thank you very much.
If evidence for life is found, will it be possible to tell whether it's an independent origin or a common origin with the Earth from exchange of space rocks?
It's a very good question, yes. I mean, we'll be able to look at, what we're actually looking for is biomarkers at the moment. So this is the sort of possibility for life. But it will be possible to do that, yes, by looking at the DNA structures and so on eventually. Now, probably not with the Rosalind Franklin mission, but with the sample return mission, if there are signs of life in there with the instruments on Earth, it should be possible to do that. So, but yes, it's an excellent question, because that's one of the big questions as to whether life might have independently arose on Mars at the same time as it arose on Earth, or has there been swapping between Earth and Mars, with meteors and so on. So, but it's more likely the independent origin, but we hope to be able to test that, yes. Yeah.
If there's CO2 on Mars, is there any reason why life shouldn't thrive on CO2? I mean, we assume that it should be oxygen, but there's no reason, presumably, that it should be.
Well, our best model, of course, is life on Earth, and that uses oxygen. So the most likely thing is that oxygen, and so that's the best thing we can look for. But of course, it's not to preclude other potential types of life. I mean, there are a number of possibilities in science fiction, in particular, about silicon-based life and all this type of thing, you know, which people have wondered about in the past, with fair scientific arguments. But of course we're looking for evidence, and the best way we can look for the evidence is for looking for evidence of life like we have on Earth. But yes, again, excellent question.
Well, I'm worried about Earth ending up like Mars before its time. And I'd like to ask if you have any estimate of the amount spent on these space projects compared to the amount spent on renewable energies and the prevention of global warming.
Well, we absolutely have to have and have to be careful about our own environment. It's really important to be studying that. So there's a lot of research going into that, and of course, energy companies actually doing that, and wind farms and so on. So there is a lot of research which is done on that. Space research is expensive, and you know, sending rockets into space and doing these amazing things which we can do on surfaces, it is costly. In the end, we're employing people on Earth to do it, so it's jobs for people, you know, high-tech jobs, keeping them from doing other things which they might be doing perhaps. And you know, what we're doing really is exploration. We're trying to understand our place in the universe, and obviously, you know, the environmental concerns at Earth are sort of part of that. One can look actually at Mars and Venus and see how those have evolved, and see, you know, with Earth, you know, and compare those and see how the evolution might go in the future. But I mean, Venus, of course, is a greenhouse effect gone mad, with very hot temperatures on the surface, the runaway greenhouse effect on Venus. And Mars, it's lost its atmosphere because it lost its magnetic field. That's not going to happen with Earth. But yes, it's very important to put money into all areas of research to make sure that we have a good environment to be working in. So yes, it's a good question. Thank you.
So linked to that, there's someone here who's asking, pointing out the amazing impression of Mars 3.8 billion years ago, and is asking how long it took for Mars to change from blue and lush to brown and barren. Yes, great question. I mean, the atmosphere seems to have been lost over billions of years, so it wouldn't have been very sudden, but certainly, you know, thousands to millions of years for things to change. So it wouldn't be instantaneous. The magnetic field losing, again, that would be timescales of thousands of years. I mean, there are models of the Earth's magnetic field. I mean, with our magnetic field, our north pole of our magnet is in the southern hemisphere at the moment. That does flip every now and again. On average, every 250,000 years in the past. Now it's been 750,000 years since the last one, so we're due for another reversal, and the signs that that's going to happen. But the magnetic field and the importance of that, you know, the timescales are relatively long. It's not instantaneous. Yes, I think, isn't it?
Efficient time to go to Mars, to send a rocket to Mars. When is the most fuel-efficient time? When is the most fuel-efficient time? Well, it's to do with when the planets line up. So Mars's year is about twice the Earth year, and so there's particular times which are efficient. So the launch window is for our mission is 12 days, and so that's starting a year today, which is just amazing to be able to give this talk today. You know, just a year before we're setting off. But yeah, we have a window of 12 days. So you have a window of sort of days to a few weeks every 2 years to be able to launch. But yes, very good question. Thank you very much. Yeah.
Well, I'm afraid that's all we have time for, ladies and gentlemen. That was an absolutely fascinating presentation. Thank you so much. And as I say, I really hope you'll come again in the future.
Thank you.
For now, many thanks.
Thank you.